An explicit equation is one that you can write as one variable in terms of another variable. So when you can write y equals and just have x's on the other side, that is an explicit equation. An implicit equation is one that shows relationships to the variables, but it's not necessarily easy to write just as one equation by itself. A good example of that is the equation of a circle. Whenever you have an x squared plus a y squared equals a number, this will be a circle with a radius of 4, whatever the square root of this side is, and a center at 0, 0. And if we have this x squared plus y squared equals to 16, we can find its derivative. So implicit differentiation is for finding a derivative when you don't have an equation that you could get by itself. And actually the circle we could technically rearrange and solve for y. And we're going to do that and look what the derivative is. And then we're going to look at what the technique for implicit differentiation is as well. So we're going to start off with our old method, saying usually when you find dy dx, you need to get y by itself. So if I had that, I could subtract the x squared on both sides, and then square root both sides. And I could get y by itself with two functions. I could get one, it's actually two different parts. One of them is the plus, and one of them would be with the minus in front. And if I wanted to find the derivative, I change my square roots to a half. Oops, almost changed it. And we could do a chain rule. So if I want to find the derivative, dy dx of this one, the 1/2 would come out in front, subtract 1 from my exponent, keep the inside the same. And then multiply by the derivative of the inside. Okay? Same thing with the other one. Bring the 1/2 out in front, subtract 1 from the exponent, keep the inside the same. Multiply by the derivative of the inside. And we actually get two different equations for the derivative. We get one equation with a negative and one equation that would be positive. Now, we were able to find the derivative because we could get y by itself. But we're going to get some equations where you will not be able to get the y by itself. So what we do is we have this as our imagination. We say to ourselves, we can't get y by itself, but I'm sure somebody could. Then they're really good at math. Yeah, they could do that. We can't, but they could. So we're going to, with implicit differentiation, and I'll do that over here, we are going to imagine somebody really smart got y by itself. And when they got y by itself, they were also very smart, knew all their derivative rules, and could take the derivative of that. They know both. They know y is equal to something, and they could take the derivative. They're very smart. And so what we do is we start off with our equation, x squared plus y squared equals 16, and say, we are going to take the derivative of the whole equation, bit by bit. The derivative with respect to x, if you had an x squared, that's just regular rules. The regular rules for that, that'll just become 2x. But the derivative for y squared, this is where we use the smart person. We said, oh, the smart person has this y all by itself with something. We just can't see what it is. But if you had to do the derivative of it and it was squared, it would be a chain rule. Because you're imagining some big thing with a bunch of x's in brackets squared. So the chain rule would say my 2 would come out in front. I would keep the inside the same and subtract 1 from the exponent. Now the inside, instead of, we don't know what it is, but we'll just say, well, whatever it is would be equal to y. And then we have to do the derivative of the inside function. Well, and we sort of cheat here too and say the derivative is just the derivative. Instead of actually figuring it out, we just keep y and we just keep the derivative part, even though we don't know what these things are. Equals, and then the derivative of 16, well, that's just a constant. That would be 0. And implicit differentiation says, even though maybe you can't get y by itself, and maybe you can't find the actual derivative when you got y by itself, you could still rearrange this to get dy dx. So, for example, can you see that I can bring the 2x over to the other side by subtracting 2x on both sides? And then I could divide both sides by 2y, and I'd have negative 2x divided by 2y. And I get that my derivative, oh, this worked out nice because it got really narrow here, is just negative x over y. And this, in yellow, is the same thing as both, whoa, there we go, as both of those combined. Isn't it a lot neater? Isn't it a lot simpler? I'll show you how they're the same, okay? You know how we solved for y and got plus or minus the square root of 16 minus x? So if I would substitute back in here and write negative x over plus or minus the square root of 16 minus x squared, because I could substitute y back into the equation. I hope that you notice, okay, let's look at these questions. Do you see that these 2's would cancel out? And these 2's would cancel out. And both of these have a 16 minus x squared to the negative a half, which would bring that to the bottom of your fraction in the square root. And both of them have an x left on the top. But one would be negative, this one's negative, and this one's positive, so you have 1 plus, 1 minus. When I substitute back in, do I not have exactly that equation both ways? But I was able to do it with implicit differentiation, with the idea that somebody smart could get y by itself, could find its derivative, and then we just use that idea all the way through without ever actually doing it, and we're able to, using algebra, get dy dx by itself. And the difference now, though, is the slope of our tangent line. In order to figure it, you'd have to plug in the x coordinate and the y coordinate at a certain point. Oh. So we can go to something for sure. Okay, spend the next 2 days trying to get y by itself. Okay, then on Wednesday, when you come to class and say, Mr. JR, I failed, I could not get y by itself in terms of x, I'm like, okay. So we need something else. But we imagine, so this is the key to this. You imagine some super genius math person was able to get y by itself. And they then could use their ingenious math skills to find the derivative of whatever that was. If we have this in our mind, we can now do the derivative with a different technique. And technically, we have, like, you know when you had something like this, 3x squared plus 5x? When we did the derivative, we just did this, dy dx equals blah, blah, blah. Technically, we were doing this. We just never talked about it this way. We were taking the derivative of the whole equation. Well, what's the derivative of y? Well, it's the derivative. And we would write the derivative of y dy dx. And on this side, you would get 6x plus 5, and you would have been 5. So the idea here that we're using more and more is this idea where we are going to just take the derivative of the entire equation and see what happens. So I actually like writing that out. So let's take the derivative ddx of this whole thing, 3x to the 4 minus x cubed y equals 15 minus y squared. And sometimes we might want to rearrange things, and sometimes we'll leave them as they are. Okay? I'm going to show you this one, leaving it as it is, and then give you a suggestion. Maybe you might want to rearrange this one afterwards, because there's a mistake that you're going to make over and over again, but I want to show it to you so that you hopefully don't make it. It's these grade 1 math, subtraction, haunts you. Negatives haunt you all through school. How many of you have made mistakes where you forgot to distribute an everybody? And it's going to happen again here. But we'll do it first this way. So, what this means, we are taking the derivative of the entire equation. Now, when you get to 3x4, that you've done all the way. That's easy. The 4 comes out in front, you get 12. X, subtract 1 from the exponent, 12x cubed. Minus. And now we have x cubed times y. So what we're doing here is wherever there's a y, we're imagining the dot, dot, dot. Some huge equation in terms of x with very complicated derivative rules. So you're imagining that right here. If you had an x cubed times by, imagine the worst, I can't even imagine that one. Not even that bad. Okay? Let's put it, yeah, let's make it worse. If you had this times this, you would have to do the product rule. Do you see that? So we're imagining where the y is, there's something with x. And if there was something with x times by that x cubed, you would have to do your product rule. So how does the product rule work? Okay? Product rule works like this. I'm tempted to do the mistake or not do the mistake. I'm going to do the mistake. See if you can catch it. Okay, product rule. Product rule says keep one the same. Keep one the same, times by the derivative of the second one. Well, what's the derivative of y? Well, the smart person figured it out and just said it's the derivative, dy dx. Product rule says keep one the same, derivative of the second, add, keep the second one the same, which is just y, times by the derivative of the first one, 3x squared. And I made the mistake. Why? Because you're subtracting all of this. When you do the derivative, that whole derivative needs to be subtracted. My recommendation to not make the mistake is rearrange your equations so if you have product rules, they're positive. And then you never have to worry about this mistake. So we'll do it again as a rearrangement at the end of the question, showing how you could avoid this mistake. Because you will forget the brackets. Equals. Now the derivative of this side, derivative of 15 is 0. And the derivative of negative y to the 7. Again, you imagine where the y is, something with a bunch of x's. Inside a power of 7. Do you see that you would have a chain rule? The chain rule would say your 7 would come out in front, keep the inside the same, subtract 1 from the exponent, and then you're going to need to multiply by the derivative of the inside. And you're like, oh, the smart person figured it out and just wrote dy dx. Okay? So this is understanding it. To keep your life easy, do you notice you're just doing all derivatives like normal, but wherever you have a y, you do its derivative like normal, like if you had a y to the 7, you get 7y to the 6, but you always have to add the chain rule. You always have to add a dy dx when you do the derivative of y. So same thing here. What's the derivative of y? It would just be 1, but then we had to add a dy dx. That's the key to implicit differentiation. It's like, you want to make it simple, just do all your derivatives like normal. Whenever you have a y, you have to add an extra dy dx when you do its derivative. But it's based on this idea of a chain rule happening, that someone was smart and got y by itself with a bunch of x's. Smarter than us, because we couldn't do it in this equation. Now, we've done our derivative of everything separately. The question asked us to solve for dy dx. You see that you have a dy dx. That's not yellow. That's back page. Here we go. We have a dy dx here and a dy dx there. And we're supposed to solve for dy dx. Well, this you can do. You have your algebra skills capable. We're going to move every term that has a dy dx to one side. Everything that doesn't have a dy dx to the other side. I know that you're smart, so I'm going to do the following. I'm going to distribute this negative all the way through, and I'm going to say I would have on this side a negative x cubed dy dx, and if I move this one over, I'd have a plus 7y to the 6 dy dx equals, and on the right-hand side, I'm going to move my 12x cubed, negative 12x cubed, and I'm going to move this negative y 3x squared, so I would add it, 3x squared y, to the other side. Once you get the terms with the dy dx on one side, you can factor them out. The dy dx is in common, leaving me with negative x cubed plus 7y to the 6. Wow. And this is our derivative. It has x's and it has y's in it. So if you wanted to find the slope of a tangent to the original graph at any point, you'd have to plug in the x coordinate and the y coordinate. How crazy are these graphs? I'm curious. So we're going to go, maybe, yes, here we go. We're going to go to Desmos graphing calculator. We are going to type in this original equation that we had to see what this graph looks like. 3x to the 4 minus x cubed y. Minus y squared. I hope it's at least a little bit exciting. Y to the 7, was it?
Yes.
That's a cool looking graph, right? Perfect. And we could even type in our derivative graph. So we found out that the derivative was this equation. Can you imagine this graph? And then finding any tangent on there, graphing all of those slopes, we get, ooh, dy dx. What do I put for that? I don't know if I can, I'll have to think about it. Oh, I have an idea. I'll steal it. Because I've got, I made a nice, here it is. All right, well, it's going to take a bit. While it's loading up, my suggestion for this question might be, as far as rearranging goes, let's put everything that has a y on one side. In particular, if you have a product rule, like we have here with the x cubed y, make those ones positive. So what I would maybe do in this question is rewrite this as 3x to the 4 minus 15 equals x cubed y plus y to the 7. If you rearranged it this way at the beginning, your product rule doesn't need to be put in brackets, and you don't have to worry about that minus sign out in front and distributing it properly. Otherwise, we had to remember the brackets here when we did the product. Oh, and I made a mistake. I saw the consternation. This would still be a minus, right? There we go. So just rearrange it, hopefully in the right way, so that your product rule doesn't have a minus sign in front. You'll make a little bit less mistakes with it that way. I'm going to see if I can look at what the derivative looks like. What? It didn't like it? Maybe this program. Does it like it now? Yes! All right. Here's what the derivative graph looks like. Woo! It's kind of frustrating. Like it goes, wait a minute. It like crosses here. Anyways, kind of fun. So this graph looks like it has asymptotes, but it actually doesn't because it crosses there. There is probably a point, especially in here, there's probably a point right here where our tangent is undefined because it's straight up and down, but then it goes backwards. So do you see that the original one is not a function? It's not going to pass the vertical line test, especially through this little part here. And that's why we get what should be an asymptote, but not actually an asymptote. Oh, I'm sorry. So I'm looking at this one. I have a product rule right here, because I have an x times a y. That'll be a product rule. But it's not negative, so I'm happy. I'm going to keep it on that side. I'm going to take the time to first rewrite this equation and say I want to find the derivative of the whole equation, but I'm going to change this cube root to 1/3. in brackets, and I put a d dx out in front, and I want to find the derivative. So in implicit differentiation, Leibniz notation is nice because the derivative is a really big thing that appears, the dy dx. You don't get lost with it. Sometimes if you just wrote a y prime, you might get confused. Was that a y to the 1, or is that a y prime? Because now I have y's left in my equation. So Leibniz notation is nice for implicit differentiation. Now, we do each thing separately. Derivative of x squared. You know that. That's 2x. Okay? The derivative of y to the third. So as a shortcut, I would say, just do a regular derivative. How do you do a 1/3? The 1/3 would come out in front. You would subtract 1 from the exponent. That's how you would normally do the derivative of something like that. But because it's a y, you'll multiply by dy dx. That's the shortcut for implicit differentiation. Again, if we want to understand what's happening, we are imagining some very smart person got y by itself, and they had the correct derivative rules to do that. That's what we're imagining. Okay? What happens then with the y to the 1 cubed, you're imagining inside something with a lot of x's. But you would have a chain rule, because the 1/3 would come out in front. You'd keep the inside the same, which will just write y, minus 1 from the exponent. And then you'd have to do the derivative of the inside. Well, the very smart person did that for us as well, and we just write dy dx. It would be really nice if we could do that for all of our math questions on any math test. There was a really smart person that figured this out, and I'm going to write answer equals ... because a really smart person figured it out. Therefore, the answer is answer. Yeah. That's the kind of idea we're doing here. Then on this side, now I have a product rule. My product rule is right here. Okay? How do I do a product rule? Keep one the same. Multiply by the derivative of the second one. Again, using the shortcut, well, that would be 3y squared, and whenever I do a derivative with a y, I add a dy dx. Using the understanding, you would have something cubed. It would be a chain rule. The 3 would come out in front. Keep the inside the same. Subtract 1 from the exponent. Then you'd have to do the derivative of the inside, which is just the dy dx. Plus, now we keep the other one the same, multiplied by the derivative of the first one, plus the derivative of 8 is 0. We take all of our terms with dy dx's. I'm going to move the 3x4 times 3y squared dy dx over to the left-hand side. And all of my terms without, so that includes the y cubed times 12x cubed minus a 2x to the other side. So what I did is I looked and I said, this term has a dy dx and this term has a dy dx. I moved them to the left-hand side of the equation. Everything that did not have a dy dx, I moved to the right-hand side. And once you have two terms with a dy dx, you can factor that dy dx out. That's going to leave you with 1/3 y to the negative 2/3. And here, minus, I guess I could put those 3 and 3 together, get 9, x to the 4y squared. And here too, I could write this. That technically would be the proper way to write it. If you left it as y cubed times 12x cubed, perfectly fine. I don't mind. If you want to write things properly, you put your coefficient, the number, out in front. You write your variables alphabetically. So you to know your alphabet. X comes before Y, but not a big deal. And finally, we can get dy dx by itself. I can't even imagine this one with the definition of the derivative. That would be insane. All right, so we're going to try some on our own. Get out your textbook.